Okay, so hi there all. We're now in our next video in number theory, and here we are on the last classical milestone. That is, we're going to talk about Euler's theorem. So before we talk about Euler's theorem, you make sure that you have watched the previous video that is talking about the Euler's phi function, or in some books we call that the Euler's totient function. Okay, we will be solely needing that in the lemmas and the concepts actually of the phi function there. Now we are ready to formally state the theorem itself. So by theorem 4.17, we let m as a positive integer, and let a be any integer. Okay, let it be positive or negative. With the GCD of a and m to be 1. That is, a and m are relatively prime. Then we say that a raised to the phi function of m, this positive integer, is congruent to 1 mod m. Okay, again, a, any integer raised to the phi function of m is congruent to 1 mod m, where a and m should be relatively prime. So let's give some examples for this Euler's theorem here. Okay, so for instance, we have here, for example, 4.18, let m be 24 and let a be any integer relatively prime to 24. So since m is 24, we need to first find the totient function or the phi function of m. Since there are 8 positive integers less than or equal to 24, that is relatively prime to 24. Namely, if we're going to state them one by one, these are the numbers themselves. So we have 1, 5, 7, 11, 13, 17, 19, and 23. So these are the numbers less than 24 or equal to 24 and are relatively prime to 24. Hence, we say that the phi function of 24 is 8. So let's just take note of that. Thus, by Euler's theorem, a raised to 24, where a is any positive integer or any integer at all, a raised to 8, that's the phi function of 24, is congruent to 1 mod 24. So actually, any a can be written here, provided that it's relatively prime to 24. It will always be true that it's congruent to 1. Okay, it's congruent to 1 given the phi function of 8, phi function of 24, which is 8. So let's give one particular example for this. So for instance, in particular, we will let A be 77. So why do we do that? Why are we doing that? Because A is equal, if A is 20, if A is 77, so therefore 77, if we're going to prime factorize 77, is going to give us 7 times 11. Then we can see that it's relatively prime to 24, since the GCD of 77 and 24 is equal to 1. So therefore, we say that 77 raised to 8 is congruent to 1 mod 24. Okay, by Euler's theorem, by the application of Euler's theorem here. We can confirm this by using some fundamental properties of congruence if we really want to check if this is indeed true, other than what we can show by Euler's theorem. So for instance, we have 77 is congruent to 5 mod 24, because 77 divided by 24, okay, is 24 times 3 is 72, or 72. So 70, the remainder is 5. So the 77 is congruent to 5 mod 24. By theorem 3.2, we have learned that in the third module, we say if we're going to raise them both by 8, that's going to give us 77 raised to 8 is congruent to 5 mod 8. Or rather, 77 raised to 8 is congruent to 5 raised to 8 mod 24 by theorem 3.2. Now, since 5 squared is congruent to 1 mod 24. Why is that? Because 5 squared is 25. 25 divided by 24 is remainder 1, or 1 remainder 1. So since 5 squared is congruent to 1 mod 24, we say then that 77 raised to 8 is congruent to 5 raised to 8 given here. And 5 raised to 8 is 5 squared raised to 4. That's the power of a power law in exponents. We're going to do that in reverse. So 5 squared raised to 4, but we know that 5 squared is congruent to 1 mod 24, therefore 5 squared is 1. So 1 then raised to 4 is just equal to 1. So therefore we say that 77 raised to 8 is congruent to 1 mod 24 as what we expected by using the Euler's theorem. Actually, we are not only restricted with 77. Any number which is relatively prime to 24 will make this um congruence true. For instance, we can use a number. For example, if we will let a as 25, which is they are relatively prime to 24. Indeed, by Euler's theorem, um, 25 um 25 raised to 8 is congruent to 1 mod 24. Okay, we can see that and we can prove that also by Euler's theorem that is true. If we're going to make use of a, likewise a, say for example, a is 31, so 31 is prime. So since we can, it's clearly that 31, the GCD of 3124 is equal to 1. So therefore, we can also say that 31 raised to 8 is congruent to 1 mod 24. And this is not only restricted with 77. So we can always use any number provided it's relatively prime to the mod, okay, which is 24. Okay, so that's the power of Euler's theorem. Let's give one more example for the Euler's theorem. This example, now, it is useful in finding the remainders of numbers involving large exponents. So even if the divisor is composite, provided the divisor is relatively prime to the base, the following example gives us this. This is example 4.19. Sorry, still loading. Okay, here you go. Sorry. Okay, so example 4.19. So we will be finding the remainder when 245 raised to 1040 is divided by 18. So getting this manually is crazy. Okay, it's very crazy to do this. We cannot do that in our normal computations. So we need to make use of some powerful theorem here. That is in particular Euler's theorem. So we'll present the solution here. So the first step in the solution would be since we say since we need to first take, since it's divided by 18, so we're expecting a universe of mod 18 here. Since 245, we need to make, or to get it, it's congruent to what number? Mod 18. What is that? Okay, what number is, what will be the remainder if 245 is divided by 18? What will be the remainder then? Okay, so we can solve that maybe by normal um division. So divided by 18, so we have 1, 18. Oops, let's move this. 18. Uh, what's this? 4, 6. Okay, that's 6. 65. Now I don't know that. 60, 18, 18, 36. Let's try 18 times 3. That's 324. That's going to give us 54. That's the one that's until what we can do it. Or 54, 54. That's going to give us 11. Okay, and pretty much this is our remainder. So 13 remainder 11. So therefore it's the mod here that we're going to write. Let's delete this. Okay, so therefore 245 is congruent to 11 mod 18. 11 mod 18. So hence um by theorem 3.2 again, 245, okay, is congruent to we'll make it 1040 because that's our original number there above, is congruent to 11 raised to 1040. By theorem 3.2, they are congruent because raising a number to a c which is constant with both sides of the congruence will still make it true. This is mod 18. Mod 18. Therefore we can therefore see that since it's clearly seen that the GCD of 11 and 18, 11 and 18 is 1, that is they're relatively prime. That is because 11 is a prime number, so it should be relatively prime to any number unless it's a multiple of that number. By Euler's theorem then, by Euler's theorem, by Euler's theorem, we say that 11, this is going to be our A, okay, raised to the 5 function of 18 is congruent to 1 mod 18. Okay, so that's where we can use the Euler's theorem here. So since 11 is our and is congruent to 245 raised to 2040, we're going to make use of this 11 to make it smaller. So we have 11 raised to the 5 function of 18 is going to 1 mod 11. Anyways, what's the 5 function of 18? The 5 function of 18 is equal to what? Let's try to solve on that. 1 is um is one of it. 2 is not, 3 is not, 4. Okay, not really. It's going to go to 2. 5 is one of them. 6 is not, 7. 8, 9, no. 10, no. 11, 12 is not. 12, 13 is a yes. 14, 15, no. 16 and 17. Okay, so how many? 1, 2, 3, 4, 5, and 6. So therefore, the 5 function of 18 is 6. Hence, we then have um, right there below. So we have 11 raised to 6 is congruent to 1 mod 18. Okay, so far so good. We have already established our congruence, and we have now defined our totient theorem, or our phi function rather, or our totient function. Now, it remains for us to get the value of 11 raised to 1040, and we're going to apply this fact here. So therefore, 11 raised to 1040 is equal to 10 raised to 6. It should be 10 raised to 6. We should make use of this since it's congruent to 1. So what are the multiples if we're going to divide 1040 by 6? Let's do that. Divide by 6. That's 1. 6 is going to give us 4. 44. Oh, what's this? 6. 7. 7 times 6 is 42. This is going to give us 20. It's going to give us 3. And 3 times 6 is going to give us 18. Um, remainder 2. It's 18. Remainder 2. It's going to give us 4. 4, 44, 42. 2, 0. Okay. So this is 173 times 6. Let's try to do that again. But it has a remainder too. So meaning, what we're going to do, let's just what do you call that? We'll just compare what do you call that? Let's just find some ways to have this remainder 2 here. So this becomes, sorry, this should be 11. My bad. It should be 11 here. 11 raised to 6. Okay, that should be 11 raised to 11, 6. So we have 11 raised to 6, all raised to 173 times, since we have a remainder 2, so that's still part of the exponents. So we will write this we'll write this as times 11 squared. That's where the remainder comes in. Well, let's continue. We know that 11 raised to 6 is equal to 1. Okay, it's equal to 1. Now, what will happen here? Let's put it in another line. Okay, this is 11. So what will happen here is that we have 1 raised to 173 times 1 squared is going to be 1 to 1. Okay. Furthermore, let's move to the next line. Let's delete this. Okay. Moving on. 1 raised to 173 is still gonna be 1. Okay, no matter what. So it remains for us to get the 121. 121 uh mod 18. Again, we are in the universe of mod 18 here. Okay, so this is congruent to, sorry, congruent to. So this is mod 18, mod 18. So since we are in the mod 18, what is the remainder of 121 if we're going to divide it by 18? So we have 121 divided by 18. We don't know that. Uh, okay, so let's try 18 times 9 times 5 is 90, times 6 is 108. Let's try 6. 6 48. This is 108. If we're going to add another 18 there, that's gonna become 1 126, which is beyond this. So therefore, what we have is 6 6 108. That's going to give us what's the remainder? Uh, what bar 7 2? That's going to give us 13. So the remainder is 13. Sorry. Sorry for the mess there. It's congruent to 18, or rather 13 mod 18. Okay, so what we have is 13 mod 18, and yeah, that's our answer. 11, okay, raised to 1040 is congruent to 13 mod 18. Going back to our first part, we said that 245 raised to 1040 is congruent to, so we can say since, is congruent to 11 raised to 1040, okay, mod 18. Therefore, since this is congruent to 13, let's use this. This is congruent to 13 mod 18. Therefore, we say that 245 raised to 1040 is congruent to 13 mod 18. And this is the remainder that we are desiring. Hence, we say, hence, the remainder is 13. Let's just do that since we don't have space. Okay, so hence the remainder is 13 when we have 245 raised to 1040 divided by 18, the remainder is 13. Okay, so imagine we cannot do that in normal arithmetic. Getting the value of 245 raised to 1040 is nearly impossible in normal calculations. Okay, it cannot fit in our calculators. Okay, so hopefully you have seen here the power of the Euler's theorem and all of the classical milestones of number theory. Again, we have started our discussion with Wilson's theorem, and then by Fermat's little theorem and Euler's theorem as its end. So this will be our last video as far as the modules in number theory is concerned. I will be creating more of this, of course, in the future, but hopefully you stick with me through the end. So thank you very much for watching, and for the last time, I hope that you would like and also subscribe. Okay? Hope you learned something from all of these videos that I've created, or more than 60 videos. So thank you very much.